speaking about probability. And if you just take a moment to remember our big picture of statistics, the point is to collect a sample or a subset of the population and use that subset to make predictions or estimates about the population. We know those are exactly that, just predictions or estimates. We're not 100% confident that those are going to happen. So that means we need to have some understanding of this idea of probability, the chance of something happening or not happening. So let's go through a few definitions in this video. The first one is this idea of a random phenomena. It always makes me think of the Muppet song. I don't know if anybody else knows that one. But anyway, random phenomena, we know the possible outcomes, but we don't know which one we will observe until the experiment has actually occurred. Let's do a couple of textbooky examples, and we'll get to some other less textbooky ones later. First one, tossing a coin. We know the possible outcomes are going to be heads or tails. And I'm going to introduce some notation. Notice I'm putting these in curly braces. And I'm also going to use this capital letter S to say, here's my sample space or my list of what I could possibly see for this experiment. The next one, rolling a dice. S is just like saying here, I'm going to list out what I could possibly see, and you're going to list that in curly braces. So if I rolled a die, I could see anything between 1 and 6. So random phenomena, we know what we could see, but we don't know what we will see until we actually perform the experiment. Now, the next thing, we want to think about the chance of seeing any of these particular outcomes. We can think of those types of probabilities in a couple of different ways. I'm going to skip over to the next page for just a moment. And the first type of probability is this idea of theoretical probability, this long run or infinite relative frequencies. So if I performed an experiment forever and ever and ever, if I flipped a coin forever and ever, I would expect it to be heads half the time, tails half the time. Empirical probability, what if I have something that's a little bit trickier? I don't really know what it is. I need to estimate it with data. So there's our key word here. Empirical probabilities are estimated from data. So let's see how these two are connected by going back to the previous page. So let's go with our coin tossing example. And for our coin tossing example, suppose we want to find the probability of tails. And we don't really know what that is. Let's pretend we just have to estimate it with data. So if I toss it one time and I get heads, that means based on that one data point, I've observed 0 tails out of 1 toss, or my estimate for the probability of tails is 0. 0% chance of seeing tails because I didn't see it on my one data point. If I were to toss it twice and I get heads again, I've tossed it twice, none of them were tails, so I'm still estimating that there's no chance of tails. It's elusive, this thing doesn't exist. If I toss it 3 times and now I finally get tails, then now I've got a different estimate for the probability of getting tails, a third. Let's keep going. I toss it 4 times and I get heads. So out of my 4 tosses, still only 1 has been tails. So now my updated estimate is 0.25. And one more time, I toss it a 5th time and I finally get tails again. So 2/5. So you can see the more data I collect, my estimates are changing. And if you think about doing this forever and ever and ever and ever, I keep going and going, then that, as I keep going forever, that probability is my theoretical probability. This short term is my empirical probability or my empirical estimate based on the data I actually observed. Now those are closely related. Notice here, for a fair coin, our chance of getting tails is about 1/2. For rolling a die, the chance of getting a 6 is about 1 out of 6. All the sides are equally likely. And I ran a little simulation, and you'll notice down on the x-axis is number of tosses. You'll notice is I have here my first toss is probably heads because my initial estimate is 0 for my probability of tails. And then it bounces around for a while, but eventually it levels off at that theoretical probability. Same thing over here, number of rolls of the die, bounces around for a while, but eventually levels off at that theoretical probability of 1/6. So we have this theorem that puts all this together, our law of large numbers. It says as we have more and more trials, more and more rolls of the die, tosses of the coin, the proportion of occurrences approaches a particular number, and specifically that theoretical value. All right, now that we kind of have a understanding about the two different types of probabilities, let's get into a little bit more of the terminology on this. So first, the next bit of terminology is this idea of sample space, which you've seen before, the set of all possible outcomes for a random experiment. So notice I'm going to use this experiment where we flip the coin twice. So sample space, it might be useful to arrange this using a tree diagram. Might be a little overkill in this example, but we'll roll with it. Our tree diagram, we're just going to set up first, we toss our coin the first time, and we've got two options. We could get heads or tails. I'll label this set of branches toss 1. My experiment's not done. I'm going to toss the coin a second time, so I'll label this toss 2. If I toss it the first time and get heads, I still have two options for my second toss. I could still get heads or tails. Same thing, if I toss my coin and get tails, I still have two options for my second toss, heads or tails. So this helps me put together my sample space. So remember that fancy S we used before represents sample space, or that list of all possible outcomes, and put it in curly braces so we can read them off here easily. Heads, 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 tails, and so on. So heads, 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 tails, tails, heads, and tails, tails. So sample space is that fancy notation writing out our possible outcomes, and a tree diagram might be a useful way to organize and figure out what those will be, especially when you have a more complicated experiment. The next definition we need to make note of is this idea of events. Events are just some subset of the sample space. So it could be just one of these outcomes. It could be several outcomes from here. So let's take a look at a couple of examples of events. And just as a heads up, I'm going to be using these events listed at the bottom of your page. No heads, at least one, and exactly 2. So event A, notice we typically use capital letters, was no heads. And the event needs to be a list of or a subset of these items. So here, no heads, that would only leave one of these guys, tails, tails. So event A has the outcome tails, tails. Event B was at least one head. And make sure you're okay with the language. At least one means one or more. So that would be outcomes heads, tails, tails, heads, or heads, heads. So at least one head, one or more. And then the last one is pretty self-explanatory. Exactly 2 heads is going to be our heads, heads. Now I'm going to use these outcomes and events in a future video, so make sure you're real clear on this, on our definition of events. So I've got 3 events. Usually you use a capital letter to denote those, and it's some collection or subset of outcomes from the sample space. Next idea is this idea of the probability of an event. So we're going to write it as probability of A. You would read that, find the probability of A. I don't know if you remember from algebra class, something like this. F of X. F is saying, well, I'm about to give you a function, I don't know, something like this. Here's a function and the variable is x. It's the same thing here, except we're going to use p because it's a very specific function. It's a function to find the probability of whatever variable or event is on the inside. So find the probability of event A. Here's a special case when all the outcomes are equally likely. This is something we've already done once in this video and you already know, but we'll formalize it here. So probability of A, when the outcomes are equally likely, is a key part again, is going to be number of outcomes in A, how many outcomes are in that event, divided by number of outcomes in the sample space. So think about earlier, we found the probability of getting tails. We said that's 1/2 because the sides are equally likely, and tails is one outcome out of the 2 possible outcomes in the sample space. Or same thing with rolling a dice and getting a 6. 6 is one possible outcome out of 6 possible outcomes on the die. So let's find the probability of each of our events above. Probability of A of getting no heads, since again the coin tosses are all going to be equally likely. I have one outcome out of the 4 possible combinations in my sample space. The probability of B, I've got 3 possible outcomes out of the 4 outcomes in my sample space. And then finally, the probability of C is 1 outcome, heads, heads, out of the 4 possible outcomes. And just a reminder, that denominator 4 is coming from up here, my sample space for tossing the coin twice. We had 4 possible arrangements or outcomes in that sample space. All right, in the next video, we're going to look at some very specific rules to go along with probability.